Morning, Nguyen. We will start the class in a few minutes, so let's wait for a few more students to join. Thank you, Nguyen. All right, let's start the class. Today we continue analyzing the pin joint truss structures. So last week we introduced two main techniques for finding the forces on trusses. The first technique was to isolate the truss by removing it from the supports. So that technique is useful when you have to find out the reaction forces. In many cases, you might get away even without releasing the structure from the support, simply by considering one single joint in the structure and try to find the free body diagram of that and solving for the forces. So um, truss structures could be very different in geometry, in loading, and also the type of analysis we do. Sometimes you're looking for the full analysis. You want to find everything inside the structure. Sometimes you're only interested in a certain forces. So there is no perfect solution. Either the study of the entire structure or method of joint, both they have the advantages, disadvantages. Um, Today, we are going to introduce the third technique that is called method of section. But before that, let's have a quick summary of the method of joint before we introduce the new technique. So, in the method of joint, in simple terms, what is method of joint? Method of joint is when you have um, a truss and you decide to study the joint as a free body diagram. So that can be done. I mean, a good example was when you had a truss like this one. All right, with the force applied here. So if I want to find, for example, forces here, I can simply um, take note that this vertical member, that is a zero force member. So if I remove that, we could then make the method of joint isolating this joint here. And as such, the force here and the force over here, these are F1, F2. And we know that method of joint only has two useful equations. Therefore, this problem is solvable. But let's draw the steps for the method of joint. First of all, you do the free body diagram of the complete truss. That is not an essential step. Only if I've been asked to find the reaction forces here, I would do that analysis. Otherwise, as I explained here, we can get away simply by studying this particular joint. But what is missing here is in my illustration, in my sketch of the truss, the labels are missing. Generally speaking, we label them as uppercase letters. So this could be A, B, C, D, E. And we never use O or I. These are confusing letters. So we simply use A to Z. And so with the support reaction, if you want to solve them, yes, I label them these as E, X, E, Y, but this is not needed for, or this one is the X. Okay. But in this case, I'm not releasing the entire structure, so this doesn't apply. The third step is, do you want to find the external support reaction in order to progress completely? In this case, we don't. The forces in each truss member. So maybe before that, you want to do some simplification. Here we did simplification. That was a zero force member. So we don't need that member here. That reduces the, I mean, it would merge AB and BE together. That becomes one single member. The force inside AB is the same force inside the BE. And the joint which I'm using to analyze, that's joint A. So here I'm applying method of joint applied at A. And then the free body diagram for that is the free body diagram. So it has an external force F. This is A. And this force is F A B or AE. Both of them are the same. And this force here is FAC. And this free body diagram is solvable because it has one unknown here, two unknown here, and two useful equations. Let me remind you that with the method of the joint, because always free body diagram will be a concurrent system of forces, it doesn't have capacity to rotate. Only two useful equations are applicable to method of joint. In another word, method of joint can only handle two unknowns. All right. So all right. Once you solve, for example, this step, I find FAC. If I decide to do, I'm talking about this step, right? On this step, if I want to proceed with solving other internal forces, I can do method of joint applied at C. And that is C. When I try to solve C, that is FCD. And then this force FCA, I don't have to worry about that because that is transferred from FAC. They are equal. So FAC and FCA, they are equal. All right. Now let's do some, you repeat the steps until all the forces you want to calculate are found. So now I ask everyone to grab a piece of paper and try to solve this problem. You want to find all forces, okay? So to find all forces, this structure from geometry point of view is symmetric, but from loading point of view is not symmetric. So I leave this question with you for 5 minutes to think about it, and then we try to take it together, all right? 5 minutes. Okay, now Chaisal joined the class. Chaisal, I want you to give this a go with this problem for 5 minutes, and then we try that together. So you want to find all internal forces in this structure, Chaisal? Thank you. A very important step here is to decide where to start. All right. My question to the class, can we start with method of joint? Can you tell me one joint which is solvable here? Can I, for example, apply method of joint at B? Let's try that together and see if that is doable. Method of joint applied at B. So I have to isolate this node, and that the free body diagram will become like this one. And just help me with writing the names. This force is FBA. This force is force BC. This force is called FBE, and that one is an external force of 10,000. Okay, question. Can we solve this free body diagram? Darcy, can we solve this one?
I
Danny,
don't think so.
can you solve this free body diagram? Yes or no, Darcy?
No.
No. Well done. Well done. Everyone listen to Darcy. We can solve here. And the reason is there are three forces, only two equations. So let's ignore that one. Or when I say ignore, that means this cannot be the first step. This is not the first step. You have to postpone that. You have to start from somewhere else. So with the very same justification that Darcy told us, method of joint at C, that cannot be the first step. It has to be postponed. What about method of joint applied to E? If I apply it to E, that still we will have four unknowns and then no input. So that one cannot be done, E. We can't start with method of joint at A or D for the very same reason. So with D, I would get three unknowns. With A, there will be three unknowns. So what should I do? Anyone can make a suggestion. We can't do method of joint at either of the joint. So is there another way to start this problem? All right, it seems we don't have any option except releasing the structure from the support. So that one would reduce the number of unknowns. And then when the unknowns are reduced, we could start method of joint at either of the support. Let's start releasing structure at A and D. So if I release this at E, I make the free body diagram overlaid on the same diagram. So here, I don't know the direction of the forces here. So let me assume that these are positive. And the next step is to label them. That one is labeled AY, AX, and this one is DY. All right. So that problem, is this solvable? It has three unknowns and three conditions, right? Perhaps the best start is to take rotation with respect to the A, and that is the positive rotation. That would vanish the rotation due to the A by AX, and then rotation due to the B external force that is in the negative direction. That's minus 10,000 multiplied by 3, which is the arm of rotation. And 6,000 also make a negative rotation. But this time, the arm of rotation is 3 plus 4, which is 7. And then dy makes a positive rotation plus dy. And the arm of rotation here is 3 plus 4 plus 3, which is 10. So that is 3,000 or 30,000 plus 21,000 plus dy, or these are minus, equal to 0. So dy is found to be 5,1 Newton. Okay, having that, we could find AY. So you got, yes, you're right. You're right. I made a mistake. This is not 21. That is 40. This is 42,000. Thank you, Nguyen. That is 8,800. And now writing the forces equilibrium in y direction, that is AY minus 10,000, 6,000, that is 16,000. All right. Yeah. So I get that. That is 7,200 for this one. Thank you, Noel. 7,200 for this one. And plus dy is equal to 0, which leads to, according to Nguyen, that is ay is 8,800 Newton. All right. And what about ax? Ax is 0 because that is the only horizontal force, right? There is no other horizontal force. Now we could start with method of joint at A, can't we? If ay is known, I could do the method of joint here, applying this force here, and this force. I mean, I'm assuming that all of them, they are positive, and that is 8,800. And this force is FAB, and this force is FAE. And the angle between these two forces are 3, 4. So that's a triangle 3, 4, and 5. So FAE times cos theta or time sine theta should be equal to 8,800. That is FAE times sine theta, which is 4/5. Plus 8,800 is equal to 0. And therefore, FAE becomes compressive. You get a negative number, and that is 11,000. Okay, and then FAB, that is FAE cos theta, which is 3/5, plus FAB is equal to 0. That is 3 times minus 11,000 divided by 5 is equal to minus FAB. So FAB is tensile. So this force is compressive. FAB is tensile, and that is equal to 6,600. All right, so now we can transfer this force to the next node. And with the next node, let me just keep FAB, which is 6,600. So I make some room here, some cleaning. All right. FBA is equal to FAB, which is equal to 6,600, and this is in tension, right? And here I have only two unknowns. So therefore, at this stage, you remember we postponed this step after finding some, reducing the number of unknowns. And now this free-body diagram can be solved because it only has two unknowns. Here, I know that FAB time, so here I got a triangle. This angle, I call this alpha. That is alpha. And then 4, 2, 4 plus 16 is 20. That is root 20. Root 20. And therefore, if I write the equilibrium of forces vertical, that is FBE time sine alpha, which is 4 over root 20, is equal to 10,000. So 20 root multiplied by 10,000 divided by 4. So FAB is 11,180. FBE. And that is intention. Okay. Now we can easily write equilibrium of forces in x direction to find out the magnitude of FBC. So that is, I just make some room here. Okay, let's write the equilibrium of forces in horizontal direction. That is minus FBA. That is minus net forces horizontally equal to 0. That is minus 6,600 plus FBC plus FBE time cos alpha. FBE, which is 1,108, and time cos alpha, which is 2 over root 20. That is equal to 0. That multiplied by 2 divided by 20 root 5,000. So 5,000 minus 6,600. And here you find out FBC to be 1,600. FBC. Okay, we found forces here, FBC, FBE. and that one. So the next step, I also have calculated this force, which is equal to that force here. All right. So at joint E, I can transfer FBE to here, that is FEB. I can transfer FAE to FEA. And then if you apply method of joint at E, there will be only two unknowns. That is FEC and FED. So this is solvable. And finally, when you get to point D, all forces are known. Or maybe before that, so the next step would be method of joint at E. The next step would be method of joint at C. And finally, when you get at D, method of joint at D, what it said, method of joint at D, you already know all the numbers. So why is that? So what can I use of that for? If I apply method of joint at D, that is a checksum. So the checksum would tell me if I made a mistake in the previous step. If everything is calculated right, applying the horizontal vertical forces, I get 0 equal to 0, 0 equal to 0. If I get something different, that means I have to go back and find where did I made a mistake. So when you do the method of joint, the last step would verify your solution. So that is when you have all, there is no unknown. Everything is known, but just checking whether they sum up properly, that is to check your answer. Okay, any question before we move on from this question? Anyone has a question here? Did you follow the steps? Just can I have a feedback? So I need to decide whether explain it again or move on. Okay, no feedback. What can I do? Let us move on. All right. So now we want to introduce another technique. So far, you remember how many techniques we had? So far, the first technique of analyzing the pin joint trusses. So you want to analyze the pin joint trusses. That means you want to find the forces inside the truss. The first technique is entire structure. Release from the support. So that one give you the support reactions. The second technique, that was method of joint. And today I'm going to introduce the third technique that is called method of section. Or that is very similar to the method of joint with one difference. So the difference is that has the same principle. And the principle is if a car doesn't move, the wheels doesn't move either. So here I have a table which doesn't move. The leg of the table doesn't move also. So that principle is easy to understand. If you are sitting inside the building and the building is at equilibrium, all bricks inside the buildings are at equilibrium. So in another word, it is up to you to choose what free body diagram you want to make. Any free diagram you make, that should be at equilibrium. So with the method of joint, what we did was we decided to isolate one joint. But what if I decide to separate my structure, making free body diagram? So here I make a section. That section is AA. So this AA, how does that reduce my system? So to split my structure into two um, separate by diagram. Let me draw this for you. The first one, I draw that in red. So remember the definition of the free body diagram. This is a virtual, this is an imaginary envelope, which is separating a structure from its environment. So that I call this the left-hand side free body diagram. Also, I can have another free body diagram, which is the envelope is developing toward the right. So here I use a different color. So this imaginary envelope should separate my structure from the universe, from its support. So that is my right-hand free body diagram. Okay, can I ask everyone in the class, grab a piece of paper and try to draw the free body diagram, the left-hand side and right-hand side free body diagram. I give you 5 minutes, and then we try to draw the same free body diagram together. Okay, 5 minutes to start now. Okay. If you're ready, we can attempt this one together. So here I have a truss structure which is fitted to the wall. And here we would like to split that into two pieces. So that there are two ways we can make the free body diagram here. So like I said, the first approach is so I do them separately here. The first one is I decide to make an envelope which is holding the right hand side. So this is my envelope. And that means I have to do one scissor at here, I have to scissor cut it here, and I have to scissor cut it at here, right? So three sections. So 1, 2, 3 sections. So that means, all right. So here I would take the left hand side and will bring that as my free body diagram. Okay, so that is the left hand side free body diagram. So this is not complete. Can you help me to complete that? First, I put the external force 1000. Second, I do the labeling. The labeling is A, G, B. And what about the internal forces has to be exposed because these are like veins. Once you cut a vein, they're going to be bleeding. So that is you expose the forces, and these forces have to be named or labeled. That is labeled as FGF. This one is labeled as FGC, and this one is labeled as FBC. All right, so this is a complete free body diagram. And now my question to Chaisal. Chaisal, how many unknowns are in this free body diagram? 40. How many unknowns are in this left-hand side free body diagram? Nguyen, how many unknowns? Yes, thank you, Darcy. There are 3 unknowns. Well done, Darcy. That is free body number 1, 2, and this is 3, right? And 3 unknowns. Is this free body diagram solvable? Darcy, is this solvable? How many conditions we have for this one? Well, um, yes, I know what you mean. Yes, Nguyen is right. This is solvable because, Darcy, the forces are not colliding at one single point. If the forces are colliding at one single force, you can only solve for 2 unknowns. But if the forces are not colliding, or in other words, this is a rigid body diagram, free body diagram. So this system, you can use all 3 conditions. The condition of net forces horizontally equal to 0, the condition of net forces vertically equal to 0, and the condition of net rotation equal to 0. So all 3 conditions are usable for here because this is not a particle. That's a real rigid body. This has a capacity to rotate. when you, Darcy, applied the method of joint, your free body diagram was like a particle. All forces collided at one single point, and then the rotation condition was not useful. That only provided you with the 0 equal to 0, which is not an answer. Do you want me to explain that again, Darcy? Is that clear? Thank you very much. Thank you, Darcy. Thank you. Now, this free body diagram is solvable. And then the other option I have is to go and do another free body diagram. Let's try both options together, and then I tell you which one is my preference. So here, the second approach is I make my free body diagram like so. So here I decide to release my structure from right hand side. And if we release the right hand side envelope, that will be like so. Well, this is not complete because it doesn't have the label. So the label, this is D, that one is C, this one is F and E. And what about the internal forces? Because you're cutting through these ones, you have to expose the internal forces. Exposing the internal forces, that is FCB, FCG, and this one is FG. So how many, oh, sorry, I forgot to include the reaction forces because that involves also releasing that from the universe. So here, D is a support, it has dx, dy, and also this is a roller support that has de, or ex, sorry, ex. So this free body diagram is not solvable, and the reason is it has 1, 2, 3, 4, 5, or six unknowns and only 3 conditions, 3 equations. So therefore, if you have to choose between I call this the right hand side free body diagram. If you have to choose between left hand side or right hand side, which one do you choose? 40, which one do you choose? Yes, left hand side is solvable, the right hand side is not solvable. Thank you, Darcy. So let's try. That is called method of section. So with the method of section, like a surgeon, you decide which part of the patient to be removed or studied. So you make a free body diagram, you just make a dissection, and that dissection, that free body diagram is like your laboratory. Inside that laboratory, you study the forces inside the structure. Okay, so there is a very interesting advantage of taking the left hand side. Apart from left hand side being the only solvable option, another advantage is by choosing the left hand side, you don't have to find the reaction forces. If my problem is only asking me a part of the answer, imagine that you are employed in a company and your boss give you this job, but your boss is not interested in all individual internal forces. Your boss only wants BC forces inside BC, force inside GC and GF. What is the quickest way? What is the smartest way of doing that? I mean, yes, of course, you can go through the method of joint, but that requires first to find the reactions and then going one by one, finding each individual force. But if you are smart, if you want to take a shortcut, Because look, your boss is only interested in these forces. They say, Darcy, Nguyen, Porty, Chaisal, whoever, can you tell me what these forces are? And in another word, your boss said, look, I'm not interested in this force. I'm not interested in that, in this, in that, not even interested in the reaction. So why should you go through extra mileage to find out those unwanted forces? So you only want to take a shortcut and find these forces in one single step. And believe me, if you solve the left-hand side 3-body diagram in one single step, you are capable of finding these three forces. Okay, who is with me? Please give me a feedback. I need to know whether to pass this slide or just repeat that. Don't be shy if you don't understand. Just let me know. I'm happy to reward it. Okay. Yes, of course, I can repeat that. Thank you for asking. Thank you, Nguyen. Thank you, Darcy. So what I said was, look, according to Darcy, the left-hand side 3-body diagram is solvable. If I solve that, what do I get? Just imagine that we went through all the calculation. When I finish solving this one by applying these three equations, I would get FBC equal to something. I get FGC is equal to something, and I get FGF equal to something, right? So anyone has a problem accepting this? So you agree with me? After solving this 3-body diagram, I am capable of finding these forces. Okay, thank you very much. And imagine that your boss only is interested in these three forces. So they pay you to tell them what is FBC, what is FGC, what is FGF. In another word, they are not interested in FAB, FAG, FBG, FCD, or any other forces. If you find them, nothing wrong with that. The only thing which is wrong is you are doing some unwanted work. You are spending some time which no one is interested in. I mean, it could be the case that your boss, in one instance, they ask you, can you tell me what the reactions are? Can you tell me what the CD is? But in this case, if this is a hypothetical situation, if your boss only is interested in FBC, FGC, FGF, the shortest way, the shortcut to answer that question is by solving the left-hand side 3-body diagram. If I ask you, what other technique can you do? The other technique never is going to be that short, is not going to be never that easy. I tell you how, otherwise I could have found these forces, all right? So just bear with me, I tell you how. If I wanted to do it in a different way, for example, imagine that these are the questions, your boss wants these three forces, but then you decide to solve that by method of joint, not method of section. So method of joint, you can just start joint here. Okay, no problem. You get FAG, you get FAB. But these are not what your boss wants. Your boss wants these three. You have to keep on. So one step you spend, you got some result, the results are correct, nothing wrong with them, but the only problem is these are not wanted values. No one is interested in these. You have to transfer the forces to B and then apply method of joint at B. Then you get a free body diagram like this one, F AB, which you transfer from that step, and then you have FBC, and then you have FBG. Okay, this is solvable, but the problem is FBG is not wanted. Your boss only wants FBC. So yes, this is not too bad. Still, you only answer one question from three questions they have. What do you do next? Next, you have to go and apply method of joint at G. And if you apply method of joint at G, eventually you will be able to find FGC, FGF. So here you took three-step solution before you can answer the question. Alternatively, if you decided to do method of section, one single free body diagram would give you all the answers you need. Is that understandable? Is that agreeable? Darcy, Nguyen? All right. Thank you, Darcy. What about you, Nguyen? Do you want me to repeat? Did you follow that, Nguyen? Thank you very much. Thank you very much. So, okay, now you appreciate the advantage of using method of section. I'm not saying that always method of section is better than method of joint. In some cases, maybe it is, like this one. It depends on the problem. It depends what you are after. If you want to find all individual forces, yes. I mean, case by case, you have to make a strategy. The strategy, sometimes method of joint is better. Sometimes you um, have to find the reaction. You would be better off with the method of section. You would be better off with the method of joint. All right, so all good. Let's go here. We decided to solve the left-hand side free body diagram. So this one is left-hand side free body. So this one we can't solve because it has 1, 2, 3, 4, 5, 6 unknowns, and that is not solvable. So we decide to solve this one, and that is a rigid body free body diagram, which you comfortably can apply 3 conditions of equilibrium, and as a result, you find FBC, FGC, FGF. So the detailed solutions are provided here. They took their rotation with respect to point C equal to 0, and solving that, the next step, they did net rotation with respect to the B equal to 0, and then, I mean, this is taking some steps, but the good thing is with one single free body diagram, you can answer all the questions. If you need the detailed step-by-step solution of that one, you can get this from the slide, which is on Canvas, week 5, the first lecture. Now, let's summarize what the procedure for method of section is. We want to give you the procedure. The procedure, like usual, you have to draw a free body diagram of the complete truss to find the reaction. This is not always needed. I mean, in the example which I explained to you before, we managed to skip finding the reactions and just finding the 3 forces which were needed. But sometimes that should be the first step. Second, with your free body diagram, you can't solve this unless the free body diagram is properly labeled with the proper letters. Proper letters means from A to Z, and you don't include I or O. They are confusing. Third step, you include the labels for the external support reactions if you decide to solve for the reactions. Then, okay, you have to make a decision. You want to find the external support reaction or not. In the previous example, we decided they were not needed. We didn't need to find the reactions. And the next decision is, do you want to solve this by method of section or method of joint? That is a case-by-case different. So you can do, if you do the method of section, it can handle 3 unknowns. If you decide to do the method of joint, it can only handle 2 unknowns per free body diagram. And then you apply the equilibrium of equation. That could be 2 conditions, could be 3 conditions. And then you calculate the forces, and then you decide whether the forces you want to transfer them to the next free body diagram. In the previous example, there is no transfer. One step found all the forces. If you wanted more forces, maybe you had to transfer the forces to the other free body diagram before you can solve them. So that is the procedure for method of section. And here we have one problem to solve. So if you are interested, I can give you 10 minutes to try that first before we try that together, or 10 minutes. So here you are interested in FBC, FBE, and FDE. So your decision is whether you go with method of joint or you go with method of section. And if you go with method of section, which section? Because there are different ways I can do the section. I can do the section here, I can do section here, I can do section there, I can do there. So which section? Let's call this AA, this one BB, this one is BC, and this one is DC. So which section would give you these three forces? So I don't want you to solve the problem and find the answer. Can you just help me with making decision which technique, whether you go with method of joint or method of section? Let's see those in favor of method of joint. I make a poll. So can you vote on this one? Okay, I got correct answer from Nguyen and Porty. You want to reconsider your answer. Method of joint, that is to Darcy is correct, Nguyen is correct. And what about Chaisal, Daniel, Flynn? Thank you, Porty. I tell you why. All right, it seems we don't have answers from Flynn, Daniel, or Chaisal. That's okay. I'm thankful to Darcy, Nguyen, and Porty to be connected or engaged. And then my next question is, okay, according to what you told me, method of joint is not suitable, so we have to do method of section. Which method of section? Is this going to be AA or BB or BC or DC? So which section you reckon is giving us the needed three forces? BC. Okay, I have two correct answers. Well done. The correct answers are coming from Darcy and Nguyen. Well done. BC is the right answer. And also, Horty, do you have any suggestion? Flynn, Daniel, Chesa. No problem. So the answer I had from Darcy and Nguyen, both of them, they're correct. The right section to give me the three forces is BC. That goes through the DE, EB, and BC. And then do I take the left-hand side or right-hand side? Nguyen, do you take left-hand side section or right-hand side section? Darcy, would you take left-hand side or right-hand side? Yes, correct. Left-hand side is solvable. The right-hand side, you can't solve it unless before finding the reactions. So for right-hand side, you have to find the reaction before you can solve this. Okay, so now I have a question for you here. Here, In this example, if I apply method of joint at E, is this solvable? If I apply method of joint at E, that means I need to take a free body diagram like so. I have to take a free body diagram like so. Is this solvable? This is not solvable, and the reason is it has 1, 2, 3 unknowns, and because the forces are colliding at point E, you only have two useful equations. All right, what if I make a method of section at AA? So AA means either left-hand side or right-hand side, but in either case, there will be 1, 2, 3, 4 unknowns. So is this solvable? This is not solvable either because you have 4 unknowns and only 3 useful equations. So I have to propose an alternative section. So my alternative section, what if I apply method of section to this one? So this one has 1, 2, 3 unknowns, and that is quite solvable. All right. So the conclusion from that is when you are making method of section, still you need to decide which section is solvable, which section is the best section to start with. So it emphasizes the importance of you have to plan before getting involved into the number crunching. So you need to read the problem, make a judgment, make a decision on how to make your. So that is the alternative solution, which is solvable. It would result in having this force, this force, this internal force, and there are three of them, three equations, because the system of free body diagram would be a rigid body, and the forces are not concurrent, and then the problem is solvable. So let's try that section here, and yeah, that I think we can do that together. So let me just grab the image and bring that to a scrap page. We solve it together there. Okay, so the decision was we decided to uh, solve the left-hand side. Okay, so the labels are there. I only have to include I have to expose the internal forces, and I assume that the external forces, that the internal forces are tensile. So maybe my assumption have to change later on, but at this stage, I can only assume that they are tensile. So labeling these forces, that becomes FDE. This one, FDB. and this one FCB. So 3 unknowns, 3 conditions, that is solvable. So what is the best condition to start? If I take rotation with respect to the point D, the advantage of that is point D, 2 unknowns are colliding over there. So for that free body diagram, I don't have to worry about rotation due to the DE, rotation due to the DB. So that is just rotation due to the CB. So CB with respect to the D, what is the shortest distance? The shortest distance is here to there. And according to 30-degree angle, that is a 30-degree angle, right? This is 30 and that is 60. So that distance, let's call this H. So H is equal to, or I can say tan 30 is equal to H divided by 2, correct? And therefore H is equal to 2 tan 30, which is 1.15. All right, so that means the rotation due to the FBC with respect to the D, if I go on with that condition, FBC with respect to the D, that makes a negative rotation. So that is minus FCB times H, which is 1.15. And then I have 2000 Newton with respect to the D, which makes a positive rotation. That is plus 2000. But the arm of rotation, that is, I have to find the line of action here. And the shortest distance between here and there, that is 2 meters. So that is 2000 times 2, positive. So from here, that is equal to 0. From here, I find out FCB is equal to 4000 divided by 1.5. So that is 1 minus FCB. FCB with respect to the D, what type of rotation? Is this clockwise or counterclockwise? FCB with respect to the D, does it rotate clockwise or counterclockwise? Because, yeah, that's clockwise is negative. Clockwise is negative. No, FCB with respect to the D, that is clockwise. Clockwise is negative. The point of rotation is D, right? All right. So then here I find FCB equal to 3464. And then the next step is I can take rotation with respect to point C. Yes, point C would vanish FDE and FCB, they both pass through the C, but then FDB, maybe it's easier to resolve that into two components. The first component is FDB cos 30, and also that one is FDB sine 30. So then taking rotation with respect to C equal to 0, I have 1000 with respect to the C. That makes a positive rotation, that is plus 1000 times 2, and 2000 doesn't make any rotation because it passed through C. FCB doesn't make any rotation, it passed through C. FDE doesn't make a rotation, but 1000 does. And also I have positive FBD sine 30. That is half. So that is half FBD. And the arm of rotation is 2. And then I have FBD cos 30 multiplied by the arm of rotation, which is H. That is in a positive direction also. That is plus FBD cos 30 is root 3 over 2. And the arm of rotation is H, which is 1.15. That is equal to 0. So by solving that, I can find out FBD. And once I have FBD, the next thing is to sum up the forces vertically, and that give me FDE. So 3 conditions we solve, and then we find the internal forces inside each individual force. So the detailed solution for that, you find that in the slide. So the slide has all the details of the calculation for you. We just did some part of that. Okay, now we have time to deal with more method of joint. Let me go back to the worksheet. And in the worksheet, just we can attempt few examples. All right, I'd rather we focus on the strategies rather than number crunching. Strategies are more challenging. Okay, so here in this figure, let's discuss this figure together. FBC, CF, FE. So that is BC, also CF, and also FE. So what is your suggestion? Should I do method of joint or method of section? Yes, thank you for the method of section. And of course, the best section is this one. And should I go with the left-hand side free body section or right-hand side section? Right-hand side. Well done, Nguyen. Well done, Nguyen. So here, what I get is the right-hand side free body diagram. And making sure that all joints are labeled. That's the second step. So the labels are already, I copy them from the question. And then I include the external force here, that is AT. At point C, there is an external force of 60 kilonewton. So what is missing here? In my right-hand side free body diagram, what is missing? So when I cut these veins, I have to expose the internal forces as external in my free body diagram. So there will be three forces here. So can you, Porty, can you help me with this one? Why should I use a subscript for this one? F, what are the subscripts? Yes, but it's better to write this as CB, starting from C to B. Yeah, that's the same as BC, but because my free body diagram is left-hand side, and I assume that this is a tensile, I put it FCB. I know that FCB, FBC are equal, but here I put FCB. And what should I label this one as? This is F. Yes, well done, Porty, CF. And lastly, this one is FEF. So the question, is this free body diagram solvable? How many questions, how many unknown? How many conditions, how many unknown? Three conditions, the forces are not concurrent. It has three useful equations and three unknowns. All right, so this problem is solvable. And can you suggest the best condition to apply here? Rotation at C. Yes, rotation at C is a good option. Also, I can apply net forces. If I apply net forces in y direction equal to 0, what can I get out of that? Yes, well done, FCF. So maybe this is an easier start, right? So this is an easier start. And then according to Nguyen, I make rotation about C. If I take rotation about C, yes, rotation about C is good. So that FCB vanishes because it passes through C, AT vanishes, and then 60 makes a positive rotation, that is plus 60, and the arm of rotation is 1. And then Okay, if I find that distance, this is the shortest distance of FDC to C, right? So that I can easily find because this is 45 degrees and that length is what? That length I can calculate. Here, that is H, and here this is half, right? So because this is a 45 degree and this is 45 degree, H is equal to, yes, you're right. You're right. I thank you for that, Porty. This is B, this is not C. So rotation about C, that is 60 times 0, and then plus FCB times 0 plus FCF times 0, and then FEF, that makes a positive rotation, plus FEF times arm of rotation is 1, and then minus 80 times 1. So therefore, FEF is equal to 80 meters. All right, thank you for that. And so we have FEF, we have FCF, and to find FCB, that is simple. To find FCB, that is net forces horizontally equal to 0, and that gives you FCB minus whatever FEF is, positive or negative. And then you have to project FCF over 45 degrees. That is plus FCF cos 45 equal to 0, and that gives you FCB. So all three unknowns are found. Let's go to another discussion for example, this problem. All right, this is a question from last week. So who can tell me whether this problem can be simplified? So let me bring that here. Okay, the question is, can I simplify this truss? Okay, which one, Nguyen? Yes, EC is a zero force member. Well done. So according to Nguyen, EC is a zero force member. And also, no, FC is not a zero force member. FC has an external load applied here, so this is not a zero force member. If there were no external force, that was zero force member. But now there is a force here. This is not a zero force member. But there should be one more zero force member here. Can you pick that up? Yes, well done. GB is also, GB is a zero force member. And then that would reduce my structure into this one. All right, is there another simplification here? So imagine I want to solve the reactions. So can you tell me if there is, simplification is not always about the zero force member. Sometimes it has to do with the symmetry. If a problem is symmetric, you can simplify the problem. Do you think that applies here? Yes, it does, because both geometry and the forces are symmetric. And as a result, I can conclude that these reactions are 30-30. Okay. Can you see that? Is that obvious? I mean, if that's not obvious to you, you still can take rotation with respect to the A and then take rotation with respect to the D. That would give you the same answer. So you can pretend these are not equal. I mean, according to symmetry, they should be equal reactions. And if they are equal, sum of equal things is equal to 60. And therefore, 60 divided by 2, that's 30-30. If you can't see that, that's okay. Just do it this way. AY dy, and do rotation with respect to the A equal to 0. That gives you CY equal to 30. And then do rotation with respect to the C equal to 0, and that gives you AY is equal to 30. Do you agree with that? Nguyen, Porty, Darcy, Flynn, Chaisal? All right. So now the problem has become more solvable. And to find out EF, EF. So if this is zero force member, I can say that FEF is equal to FED. Do you agree with that? Also, I can say if this one is a zero force member, I could conclude that FGF is equal to FAG. So that means all I need to do is yes, I need to apply method of section to, this is EF, CF, and BC. So I make my section here, and then either the left-hand side or right-hand side, both of them are solvable. So then my free body diagram would look like this one. So this left-hand side free body diagram, that is solvable because it has 1, 2, 3 unknowns and 3 conditions. So the best condition to start with, I mean, you can apply net forces vertically equal to 0, and that easily give you FCF. And for that, FCF would be in compression, not in tension, because both vertical forces are upward. So I had to change this one as a compressive. So this equation gives you FCF. And then you apply net rotation with respect to the C equal to 0, and that gives you FEF. And finally, you apply net translation in the horizontal direction equal to 0, and that give you FCB. Okay, so today what we did was we went through a summary of analyzing techniques for a truss structure, pin joint truss structure. The first technique was solving the entire structure. That is most useful to find the reactions. The second technique was method of joint. Method of joint is simple, but it can only handle two unknowns at a time. It means choosing the first step for method of joint can be tricky. Sometimes maybe you can't start with method of joint. You have to start with entire structure before you can do the method of joint. And even with that, there should be a certain procedure. So you have to decide which joint is solvable. And then by solving that, you transfer its identified forces to the next step to reduce the number of unknowns. And then you keep going until all forces or the required forces are determined. Also today, we introduced the third technique, that was method of section. And method of section is particularly useful when you only are interested in few internal forces, not the entire forces. And the feature of that is a free body diagram from method of section. You have to choose it splits the structure in two pieces. You have to choose which split is the best one to start with. And it can handle three unknowns because by making a section, generally speaking, you ending up with a rigid body free body diagram. And rigid body has not only capacity to translate, also it has capacity to rotate, and it has three useful equations. All right, so just bear with me. Let me finish the attendance, and then I'm happy to take any question you might have. So Sehrish is away. Natasha is away. Nguyen is here. Chaisal was here. Daniel was here. Abdullah away. Jonathan is gone. Ahmed away. Nijil away. Barnaby away. Flynn is here. Shah away. Darcy here. And Porty here. All right. So that is all I have for today. If there is a question, I'm happy to take your question. Okay, no question. Thank you, everyone. And I look forward to see you in tomorrow demonstration class. Take care. Thank you. Bye, Porty.